Welcome to this lecture on Microprocessor 8085 introduction. In this lecture, we will be discussing about the architecture of microprocessor, in which there will be introduction, the history, features of 8085, then block diagram and the pin diagram. So let's start. First, we define what a microprocessor is. A microprocessor is an assembly of digital circuits that can perform multiple operations in very low time of the order of few microseconds. It is the fundamental unit of microcomputer system. One thing to understand here is that the digital circuits assembled in a microprocessor do not work at their own but need to be activated by feeding binary codes, which are provided with the help of an input device like keyboard or some other input device. So the types of microprocessors will see that there are different types of microprocessors depending on the technology used and the strength of instructions. It's a well understood fact that the power of a microprocessor depends on its powerful instruction set. The instruction power is again related to the number of bits in a microprocessor. Hence, the most common categorizing of microprocessors is carried out with its internal bit structure. Although the processors are explained from the bit structure of 4 bits, but the first useful microcomputer was designed with 8-bit microprocessor. Intel is a big name in microprocessors. American company Intel Corporation is a unique name as regarded the development of microprocessors. Although some names like Britain Zilog, again American Motorola, also figured in the early development of microprocessors, but Intel took over the world market, leaving all others far behind in the competition. 8085 and 8080A were the first 8-bit microprocessors developed by Intel. If we look on the evolution of microprocessor chips, we start from the early 70s. The 4-bit processor 4004 in 1971, a 4-bit bus processor, 4-bit data bus processor with 8-bit address. But then later on we'll see that we go in the various development stages of the microprocessors and we reach i3, i5, i7 in 2010, and you see that we move from 4 bits to 64 bits. Again, if we see a glimpse of technology change up to about 2000 or around, so we are having this the increase, the straight line increase in the devices per unit area of microprocessor chips. You see the development from 4004 to Pentium and then advanced microprocessors. See that we move from 0.01 MIPS to 500 MIPS, and you see that with transistors of 2K or 3K we move to the transistors beyond 10 million per unit area. Let's discuss about the functional block diagram of a microprocessor. Then the microprocessor will see that there is a main active register in a microprocessor we call as accumulator. The accumulator in the sense is controlling all processes which are carried out through the microprocessor. So this accumulator need to be connected to the structure, internal bus structure of the chip. So it's internally connected bidirectionally to the internal bus so that the data can come and data can leave from here. And again, if accumulator has to do everything, then it needs to have its neighbor register while performing operation on data. It needs to have a temporary register with which it can work on the data. So again, how it works on the data, there's an important unit, arithmetic logic unit in the microprocessor, which is connected to this accumulator, and in turn with it is associated temporary register also. So what it is going to do is that whatever data is to be processed by the accumulator, it processes it with the help of the arithmetic logic unit. So all arithmetic and logic operations are carried out in this, and then for this arithmetic logic unit there is a indication that what is the status of the arithmetic logic unit or the accumulator in the other sense. And you see that these are indicated by the flags, like what are the contents of accumulator. If they are 0, a flag will be there which will indicate that the contents of accumulator are 0. Or if a carry is generated after an addition or multiplication, or we say that multiplication actually is the repeated addition, means that if a carry is generated, a carry flag will get activated. In the same way, if there is a operation in which the accumulator contents will be 0, so there is another bit which will get activated, that the contents of accumulator are 0, that is represented by another flag, another bit called Z flag, 0 flag. So there are various up to 5 flags in 8085. We'll discuss it later. So what else is required for the accumulator to carry out operations is that it needs to have the data anywhere. One thing that since there's no internal RAM available inside the microprocessor chip 8085, so what is to be done, that if we have to just store the data, it is to be stored outside. So when the data is to be stored outside, so it takes ample of time to get that data to the accumulator. So it needs some sort of RAM inside, a very little RAM inside, and that is being provided with as multiple registers, and those multiple registers are a pair of temporary registers WZ, which is not available to the user, as temporary registers are not available. These are used by the microprocessor internally for its own. And then the BC pair is a B register and C register, individual registers, as well as that they can be paired also. So then there is another pair D and E, and then there is H and L pair. Then there is Again, another important register what's called a stack pointer. What stack pointer is, it actually that keeps the address of the stack. It's a pointer. It's actually used as an address storage of a stack. So then there's another important register, very important register, program counter. What program counter does, actually pointer stored is the memory, pointer stored is the RAM, and then to it is associated a increment decrement register. Then we have the address bus, and also we have the bidirectional data bus. The address goes from the program counter in the unidirectional, means pointing towards the memory, but then the same bus AD0 to AD7 is used as a data carriage bus to connect to the internal memory of the microprocessor. If the program counter connects or points towards the memory in the RAM, then the operations of the read data or write data, which is provided through the instruction, actually according to that the data will flow, and the data will flow through the lower part of the address bus, what is called address data bus, 80 to 87. The data will flow from the memory towards the internal data bus, and then accordingly it will be stored or processed, whatever is to be done. So then a very important thing is that we have an important register, what is called the instruction register. What instruction register is, that it takes automatically the instructions. If the program is stored, suppose the program is stored in the RAM, then when the program flows towards the microprocessor, the first data byte is taken as the instruction. So the instruction register fetches this data of instruction and decodes it, and when it decodes it, it generates control. So there is a control unit in the microprocessor, and in the control unit we have different sections. We have a clock generation section, in which we have two crystal connections, quartz crystal connections, x1 x2. Then we have a clock out signal which is given to the other devices outside the microprocessor, and then we have the control signals. In the control signals we have ready, we have RD bar, read bar, and then similarly we have in the control signals write bar, and we have IOM bar, means input and memory. These are the controls, 4 control signals, and there are status signals S0, S1, and ALE, address latch enable. These are used, the stat pins are used for controlling the address process. And then we have DMA, direct memory access, means if we always try to transfer data through microprocessor, it may take a long time. And what is that a DMA device is connected, which actually asks the microprocessor that it has to transfer data into the memory. So it gives the control to the device, and so the data is given to the memory directly without involving the microprocessor operation. That means the data transfer now will be fast. So in this we have two signals. The whole signal comes from the DMA device outside, and the microprocessor gives the acknowledgement to this whole signal that I have I'm allowing you to transfer data to the memory. And we have the reset signal as reset in, a signal which will reset the microprocessor internal chip, and then the reset out if the outside device is to be reset by the microprocessor if it wants at any place to synchronize with the outside device, so it gives a reset out signal. Then we have the different controls which are generated by this timing and control section, and they are internally connected to the various devices inside the chip. And then we have the important section what's called the interrupt control. The microprocessor generates interrupts and it actually serves interrupts. The interrupts actually come from the outside devices, and they have to interrupt the operation of the microprocessor, and there are various interrupts. Those interrupts are the signal from the outside device. So the lowest priority interrupt is INTR, and it is acknowledged by a signal what is called INTA. This is the lowest priority interrupt. Then we have RST 5.5. It's maskable interrupt of the lower priority. Then we have the more priority RST 6.5, and we have again more priority to RST 7.5, and the most priority, the first priority interrupt is trap. The trap is non-maskable interrupt, and whenever it is given to the microprocessor, it stops altogether other operations and serves the trap request first. So then there are last device what we have to say, that serial input and output control. That means it has a serial data processing inside the chip. So what if we can give direct serial data to the microprocessor through a signal called SID, and we can take out data from the microprocessor serially with the help of this pin, what's called SOD or SOD, serial output data and serial SID, serial input data. So in total, if we see that there are 14 timing and control signals, then there are 6 interrupt pins, and this make 20. Then SID and SOD make 22. Then 2 power signals VCC and VSS makes it 24. Then we have the data bus, data address bus, and address bus, higher order address bus. These are 16 pins. Then 24 plus 16 means the 40 pin chip. So the microprocessor is a pin chip. This is the pin diagram of 8085. We have the VCC and VSS at 20 and 40, and then if we start from the first, we have the clock connections at 1 and 2. 3 is for ready out. Then the serial input, serial output data on 4 and 5. Then we have the interrupts from 6 to 11. Then we have the address data bus up to 19. Then we have the higher order address bus A8 to A15 up to 28 pin. Then we have the status signals S0 and ALE. Then we have the control pins write and read. Then again S1 the status pin. Then we have the ready this control signal IOM bar, and then we have the ready signal of the control signals. We have the reset in and the clock out of the crystal section, and then we have the hold and HLDA for the DMA services. So this is the all pin connection of the 8085. So with this we come to the end of this lecture. Thank you very much.